Okay, now we are going to consider an example to apply to see how we can calculate error probabilities. So first, let's think about Bayer aspirin. The smallest dose of over-the-counter aspirin is 81 milligram, like to my knowledge. So anyhow, it does not matter in our example. So consider this medicine, and so suppose that you are an FDA agent and you want to test if this medicine, this brand, contains the correct dose. You'd like to verify, confirm, inspect if the dose is correctly produced. So your hypothesis to test are given this way. So the null hypothesis is the medicine is good in the correct amount. So 81 milligram, and the alternative is negation of that. It's wrong. It's not 81 milligram. So of course, mu here is, mu stands for the expected amount of aspirin in a randomly chosen pill. Like if you choose one and measure how much aspirin is contained in a pill, and it should be 81 milligram, but there can be like measurement errors and some manufacturing errors, so we assume that it is random. So it is the amount is random, but it should be, its expected value should be 81 milligram. Okay, and then you like after setting up the hypothesis, you collect data. You random sampled 100 pills and measure their amount, their dose, aspirin dose. And simply for simplicity, I will assume that the measurement errors are known. I mean, you know the measurement errors have a standard deviation of 5, right? 5 milligrams could be so a standard deviation of 5 milligram can happen during the process of measurement, right? And it's fake numbers, so it's not based on any medical facts, so do not take it too seriously medically. Anyhow, standard deviation is 5, so and we are going to set the significance level at 5%. And then first you need to calculate the critical values. Try this. Pause the video and think about the calculate critical values. Okay, the answer is like this. So we used 5%. So the z value that corresponds to 5% is 1.96. It is top 2.5% value. So this corresponds to 5%, and we have used this number many times already. And then, given this, the critical values are calculated this way. First, mu0 is your hypothesis. Your hypothesis is 81 milligram, and like from the amount should be like the expected amount is 81 milligram, but due to measurement error, you are going to allow a certain margin around 81 milligrams. So 81 plus minus a certain margin. This margin is calculated like this. Z value is 1.96 and multiply standard deviation 5 and sample size is 100. So if you calculate that, you allow plus minus 0.98 milligram. That's the margin of error for the sample average. And then as a result, the critical values are 80.02 lower side and 81.98 on the upper end. So you are going to, say you are an FDA agent, and if you random sampled one aspirin, and if you find its measurement is within these two numbers, then it's okay. However, if you find that the sample average of 100 pills is smaller than 80.02 or greater than 81.98, then it's a problem. It is significantly different from the label amount, 81 milligram. So the dose is incorrect. So the FDA has to do something to stop, ban it or do something. Anyhow, so that's how it works, or what we imagine in this example. And okay, that's that. This is what we learned in the earlier chapter. Now we are going to calculate the error probabilities based on these critical values. Remember, we learned critical values are useful when you can apply the critical values to many different data sets, right? We are going to imagine exactly like that. So you can use different, you can test different brands or at different points of time, or the same medicine product produced at different factories, whatever. So you are going to apply the critical values for many data. And then what we are going to do here is, first we will consider type 1 error. Type 1 error is, by definition, is rejecting the true null hypothesis. So type 1 error happens when you reject the null hypothesis, but it was actually true. It was actually correct, but you rejected it by mistake. So we are going to calculate this probability. How much can this happen? So first, let's think about each of these two, the meaning of these two phrases. Rejection. Rejection of the null hypothesis happens if the sample average is too small, smaller than the lower critical value, or too large, greater than the upper critical value. And you know the values of the critical values. So you know when the null hypothesis is rejected. You can interpret this in this phrase like this. And when the null hypothesis is true, that means the true mean is 81. So the true mean is 81, but sometimes due to the randomness, your sample average may be too small or too large. How likely is that? You can calculate it this way. Type 1 error is this probability, the probability of the average being too small, or the probability of the average being too large. Alright? Exactly. This is the probability of rejection. And of course, you know the distribution of X bar. So calculating this probability is possible. But remember that we are using this assumption. We assumed that the true mean is 81 milligram because we assumed that the null hypothesis is true. So let's calculate. It's what we did in what we learned in the sampling distribution chapter. How can we do that? So by the central limit theorem, we know X bar follows a normal distribution, and the parameters are the mean is given by the assumption. The null hypothesis is true, so mu should be 81. And the standard deviation and the sample size are known, right? The numbers are given, so 0.5. Then, using those two parameters, you can standardize X bar in the probability. So this probability can be standardized in this way. Subtract mean and divide by the standard deviation, and which will be z smaller than minus 1.96. And the other side will be symmetric, probability z greater than 1.96. And then again, type 1 error probability will be sum of these two probabilities, which will be 5% in the end. One thing you can you need to note here is that so far I did not say what is the realized value of x bar. It's because x bar is treated as a random variable. So that means we do not fix x bar to one realized value. We do not it can take many different values because it is random. So the realization of x bar is not needed. So it's like we are calculating what is the probability of like wrong rejection. Okay, that's one thing I want to say here. And another important thing, more important thing here is that type 1 error probability always equals to the significance level. The result is 5%, right? 5% is actually the significance level we used to define the critical values. So because the significance level was 5%, we had 5%, and this is coming from these numbers. You must be familiar with these guys, 1.96. So it's not a coincidence. It happens all the time. Because that's the secret is in the formula for the critical values. Critical values are calculated this way. This is the formula. But during the process of calculating the probability, you need to standardize it, right? You will be standardize it again. Then it will be standardized in this way. Subtract the mean and divide by the standard error. Then it will be cancelled out, and it will be cancelled out. And in the end, it only has z value. Then by construction, the probability outside plus minus z alpha over 2 is always alpha over 2 in each side. So probability from the bottom is alpha over 2. Probability from the top is also alpha over 2. So if you sum them, always alpha. So this holds all the time, right? So remember, why does it happen? I can connect them this way. The null hypothesis, remember, the null hypothesis is rejected when the p-value is smaller than alpha. P-value is, remember, p-value is, so if you rank all the possible outcomes from the most suspicious to the least suspicious, p-value is the probability ranking. How much percentage with like you are on the top, from the top. And alpha is the percentage you are going to reject, right? And so if you increase alpha, that means you are going to reject more on the top, right? 1% is like this, and then 5%, and then 10%. So higher alpha implies more rejections by construction. And then remember, type 1 error is rejecting a correct null hypothesis. Type 1 error happens only when you reject the null hypothesis. If you do not reject the null hypothesis, then type 1 error never happens. So if you reject more, then automatically type 1 error will increase. Because more rejection, when you increase the number of rejections, some of the additional rejections may be rejection of a correct null hypothesis. Then they will increase the number of type 1 errors. So higher alpha increases the type 1 error probability. And in the end, actually, they are the same thing. Significance level equals the probability of type 1 error. And some textbooks simply define the significance level as the type 1 error probability. So I defined significance level in comparison with the p-value. This is one possible way to kind of introduce what is significance level and what is the p-value. But other textbooks introduce the significance level just by saying that it is the error probability, right? So it's so anyhow, the point is it is always true, right? You don't need to calculate type 1 error probability. In the next video, I'm going to introduce how to calculate type 2 error probability. It will be a little more complicated. Okay, see you in the next video. Bye.